Welcome to another Mathologer video. After the last insane Mathologer marathon, in which Marty and I proved that E and pi are transcendental numbers, I needed a bit of light relief. And maybe you do too, right? So how to relax? Well, we'll have fun with some of the most spectacular mathematical vanishing and materializing paradoxes, tricks and illusions. This video was inspired by physics student Bill Russel from Bakersfield, California, who contacted me about a new type of vanishing paradox. He chanced upon this paradox while considering magnetic fields, spring constants, and playing with a mysterious object that features on the Mathologer channel page. That curious, blurry, bubbly thing over there, what is it? Well, let's see. Pretty cool, isn't it? It's called a Toroflux or Torofluxes or flowing torus. It's an amazing toy, a long flat ribbon of spring metal coiled into a very special closed helix. When draped around an arm or a rope, its overall shape can be seen to be essentially that of a bagel or, in Maths lingo, a torus. The bending energy of the spring metal makes it cling to the rope, and oriented like this, it will slowly start rolling down the rope. As it does so, it will rotate both around the rope and around the circle at its core. You can see what's happening in this animation taken from a great Toroflux blog post by Los Angeles physicist Danil. The Toroflux is also very interesting for mathematical reasons, and I'll say more about that at the end of this video. For now, let me just show you the amazing property that Bill stumbled across. Let's count the number of coils. All right. 13. Great. Now collapse the Toroflux and let's count the number of coils again. All right. Okay, count, and what do we got? 14. One more than previously. What's going on? Where did the additional coil come from? I'll explain this paradox later on, but first let me tell you about some of my other favorite appearing and disappearing tricks and the mathematical magic that powers them. Time for some fun. Serious fun. Okay, let's start with a classic, powered by the Fibonacci sequence. 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc. You all know the sequence and may be sick of it, right? But anyway, begin by choosing one of the Fibonacci numbers, say 8. Next, make an 8 times 8 square. Now, 3 and 5 are two Fibonacci numbers that come before 8, and so they add up to 8, right? We can use 3 and 5 to cut up the square like this. Here is one of the segments of length 3 in this dissection, down there, and here are the other ones. So it's really crawling with these things. And here are all the segments of length 5. Okay, now rearrange those 4 pieces into a rectangle like this. Neat, huh? Notice how the 3 unit segments pair up nicely in the middle, okay? So it all fits together nicely. For what comes next, I better show you how this rectangle and the square we started with in one picture. Okay, time to calculate some areas. How about the square? Well, that's a hard one. Well, 8 times 8, that's 64. How about the rectangle? The short side is 5. And how about the long side? 5 plus 8, that's 13, the next Fibonacci number. That means that the area is 13 times 5, and that's 65.
Hey! What?
Amazing, huh? Just a little cutting and rearranging and we get a larger area. Where did the extra area come from? It gets even more unbelievable. Notice that all our cutting and pasting was based on the Fibonacci number 8 and the 3 neighboring Fibonacci numbers 3, 5 and 13. It turns out that similar magic can be created by any other Fibonacci number. For example, let's begin with 13 and its Fibonacci neighbors 5, 8 and 21. Then our cutting and rearranging creates this square and rectangle here. Okay? And the areas are, well, 13 squared at the top, that's 169. All right. And 21 times 8 at the bottom, that's 20 times 8 is 160, plus 8 is 168. what? Instead of gaining a unit square, this time we've lost one. Are you amazed?
I'm amazed.
Oh, he's amazed. Okay. What's going on? To recap, starting with an 8 by 8 square, we gained 1 unit square. Then starting with 13 by 13, we lost 1. What's next? Well, maybe you can guess. Starting with the next Fibonacci number 21, it turns out that again we gain 1. And after that we lose 1, and so on. Okay, so what's happening here? Well, first of all, it's time to fess up. We cheated.
What?
You shocked?
Oh,
my God. Of course, without cheating, the areas before and after must be the same. Here's the rectangle drawn without the thick black edges, and you can probably guess now what's happened. As you can see, the rearranged pieces don't quite fit together, which was previously hidden by the thick edges. In fact, the pieces leave a thin sliver along the diagonal uncovered. That sliver has exactly area 1. The extra bit which makes the total area apparently jump from 64 to 65. Cheeky, huh? In the next instance, where we lose a square, sliver by sliver, the non-cheating picture looks like this. A bit harder to see, but this time, instead of a gap, there's a very thin overlap along the diagonal. Let me highlight it for you by pulling things apart a bit. So, pull apart, just wiggle a bit. Okay. So our Fibonacci magic boils down to cheating, but it is really magical, really ingenious cheating. But of course this is Mathologer, so even in a relaxing holiday video I can't just show you a mathematical trick and then wave my hands in the air. I've actually got to show you why it is true. But no real mathematical seatbelts needed for this one, just hold your coffee steady, okay? So here we go. As we've seen already, the fact that our 4 puzzle pieces almost fit nicely together comes from, you guessed it, the way Fibonacci numbers work. The fundamental Fibonacci fact that 2 consecutive Fibonacci numbers sum to the next one. Algebraically, the plus or minus 1 difference in areas is the difference between a Fibonacci number squared and the product of its 2 neighboring Fibonacci numbers. This fact has its own name. It's called Cassini's identity. It is named after its discoverer, the mathematician, astronomer and engineer Giovanni Domenico Cassini. You may be familiar with the Cassini space probe. Well, it's the same Cassini, okay? Anyway, we can write Cassini's identity like this. Or, to be more precise, we can rewrite the right side to capture the alternating plus and minus like this. Cassini's identity shows why the Fibonacci puzzle works, and while preparing this video, I stumbled across a really nice pictorial proof of Cassini's identity, which I just have to share with you. Here we go. Start with a unit square and place another unit square next to it. Now place a square on top. What's its side length? Well, obviously 1 plus 1 is 2. Now attach a square on the right. Side length, 1 plus 2 is 3. Square on top. Side length, 2 plus 3 is 5. And so on, alternating between attaching the squares to the right and on the top, okay? There's 8, 13, 21, 34. Well, obviously, the sequence of squares is a very pretty geometric counterpart of the Fibonacci sequence. Let's now look at 2 consecutive squares there. And let's calculate the combined area of these squares in 2 different ways. The first is the obvious one. Just calculate the area of each square and sum. That gives 13 squared plus 21 squared, okay? For the second way, we consider the total area as the sum of the areas of 2 rectangles. Okay, there they are. First the large rectangle. So that's one with area 34 times 13. And what about the smaller one? Well, let's have a look. Its area is 21 times 8. Almost done. We just have to rearrange a little. Move the 21 squared to the right side and move the 21 times 8 to the left. Okay, here we go. To finish, we make things look a little more symmetrical by pulling out a -1 on the right side. Okay, what this says is that the 2 consecutive Cassini differences only differ in a minus. And the same is true for any 2 consecutive Cassini differences, For example, repeating our calculation for the two green squares gives this, and so on. And so we know that all Cassini differences have the same size, just alternating in sign. And so simply verifying that one of the differences is 1, which is completely obvious, right, proves Cassini's identity at all levels. How super nice, pretty was that? Now, just in case you know some matrix algebra, there's another really cute way of proving Cassini's identity based on the matrix equation over there. This identity allows you to calculate the Fibonacci numbers just using powers of the 1110 matrix on the right. Puzzle for you. This matrix identity is just one step away from Cassini's identity. What's that one step? Well, if you know, tell us in the comments. And here's one more challenge for you. Calculate the area of the big rectangle in two different ways to come up with another interesting Fibonacci identity. Okay, that was a great appearing-disappearing trick, but of course it involved cheating. On the other hand, if you're a master of infinity, then you can make things appear and disappear without cheating. Let me just show you one nice simple example of this sort of mathematical magic. Over there is an infinite half plane. So what you see there is supposed to go on forever in this direction, okay? Let's now make two parallel cuts like this. Take the resulting infinite strip and move it to the right. Slice off the square there and make the cuts invisible again. All right, so we end up with our original half plane plus an extra square. And we created this extra square just by making 3 cuts and rearranging the resulting pieces. Very simple and pretty amazing when you think about it. Was this cheating? Nope. That's simply the way infinity works. As some of you will know, there are many more such infinity tricks, much more impressive than our slicing trick. If you're interested in some highlights, definitely check out the Vsauce video on the Banach-Tarski paradox and the Mathologer video dedicated to these sorts of infinity paradoxes. Okay, back to Planet Finite and time to start zeroing in on the Toroflux. And there's still more tricks to see along the way. Over there, I've drawn 13 line segments. Now watch this. Whoa, all of a sudden there's only 12 lines left. Where did that 13th line go? Well, there it is again. Now, many of you will have guessed the trick, but the same basic trick can be much better hidden. Here it is using people instead of lines. There are 8 baseball players to start with. Now watch this. Let's count the players again. 9. One more player. Pretty cool, isn't it? Here's another really famous and moderately racist example, the get off the earth paradox. What do we see here? Well, 13 Chinese swordsmen arranged around the globe. Okay, there's 13. Now let's turn the globe and everything on it. All right, let's count the swordsmen again. And we get 12. One's gone missing. Okay, let's make him appear again. There, 13 swordsmen again. In fact, if we keep rotating in the clockwise direction, we can get more swordsmen. 14, 15, well, those guys there at the bottom are getting a bit iffy, but anyway. The Get Off the Earth puzzle was published in 1896 by Sam Loyd, the Erno Rubik of the 19th century. Sam Loyd was incredibly ingenious and prolific, the creator of many puzzles that are still puzzling millions of people today. His Get Off the Earth puzzle sold over 10 million copies, and Loyd is also responsible for popularizing the Fibonacci cheat that I showed you earlier, and the super famous 1450 puzzle that I already talked about in another video. Many of Loyd's puzzles were based on simple principles, just really well disguised. His Get Off the Earth puzzle, for example, is really no different than our lines paradox. And here's the simple explanation. No individual line vanishes or gets created. What happens is that this red cut here creates 12 line segments above the red line and another 12 below. Then the 12 below are recombined with the 12 above to form 12 new lines, each a little longer than the ones we started with. The increase in length of the individual lines is barely noticeable, but of course these little increments together sum to exactly the length of each of the original lines. More generally, the vast majority of geometric vanishing or appearing paradoxes are based on the cunningly disguised redistribution of length, area or volume. That's true for all the paradoxes that I discussed so far, and it's also true for the Toroflux paradox. Remember, expanded like this, we count 13 coils. Collapsed, we count 14. It's actually not surprising that there's a difference. Remember that if you just give the collapsed Toroflux a little bit of a nudge, it expands all by itself. In particular, all the coils expand. However, the steel wire definitely does not expand, so the total length of all the coils must remain the same. And so, if our coils have grown larger, we should not be surprised that we've also ended up with fewer coils. However, unlike all the other real-world paradoxes we've discussed, the Toroflux transition between the collapsed and the expanded state is continuous. Doesn't this strike you as strange? How can you possibly move continuously between 13 and 14 coils? Surely you either jump or you don't, right? There's definitely something extra paradoxical about our Toroflux paradox. I already mentioned that when you drape the Toroflux around something like a rope or your hand, then overall the Toroflux will look like a torus. That's of course where it gets its name from, right? In fact, the Toroflux is what mathematicians refer to as a torus knot, a closed loop that lies on the surface of a torus. There are infinitely many different torus knots. Here just 3 examples. This one is not very knotty. It's basically just a slinky with its end joined together, okay? All right, then the next one is definitely knotty but not so windy. It's called a trefoil knot, for pretty obvious reasons, right? Finally, here's an example that's very windy, very knotty, and very rainbowy. Okay. Any torus knot can be pinned down by 2 numbers. The first number is the total number of times that you wind around the ring of the torus as you travel around the loop. For example, for the slinky, this number is 12. How can we see this? Well, moving from here to here, we've looped once around the torus. And so the number of times the slinky winds around the torus just equals the number of points on the outer equator. And that's 12 for the slinky. In the case of the trefoil knot, this number is 3. And for our windy, knotty, rainbowy example, the number turns out to be 15. The second number associated with the torus is the number of times you loop around the point in the very middle, as you travel once along the knot. In the case of the trefoil knot, this number of revolutions is 2. Well, let's convince ourselves of this. Okay, once around, here we go, and a second time, and we're back to where we started from. Great. What about the slinky? Well, obviously, here the number is just 1. For our complicated knot, this number is 7. Okay, now, here's a nice idea. A couple of videos ago, I talked about the possible orbits of moons of planets revolving around the sun. I had the planet and the moon always moving in the same plane, as they do. On the other hand, if the circular orbit of the moon is at right angles to the orbit of the planet, the overall orbit of the moon around the sun will be a torus knot. If we do this with the moon over there, then the moon's orbit is our slinky knot. Nice, huh? So in the sun-planet-moon model of torus knots, our 2 numbers just count the number of times the moon orbits the planet and the number of times the planet orbits around the sun as the moon completes one full journey. Now, it's not too difficult to see that the 2 numbers of a torus knot are always relatively prime. That is, they don't have a common factor different from 1. In our examples, this amounts to 2 and 3 for the trefoil knot being relatively prime, the same for 1 and 12 for the slinky, and also for 7 and 15 for the complicated knot. As another challenge for you, prove this relatively simple, relatively prime fact in the comments. Also, given any ordered pair of relatively prime numbers, there's a torus knot with these numbers as the knot's numbers. Of course, unless the 2 numbers are both 1, corresponding to the world's most boring torus knot, being relatively prime means in particular that the two numbers of a torus knot must be different. Okay, what then are the numbers of the torus flux? Well, perhaps you've already guessed. The first number, the number of times the Toroflux coils around the torus is, well, let's count it again. There we go, 13. All right. Then, collapsing the Toroflux doesn't change the number of times the wire winds around the middle. And so the second number is what? Well, let's remind ourselves, 14. What this means is that when we count the coils of the Toroflux before and after the collapse, we are really counting two very different quantities. This also becomes apparent if we perform the collapse really, really slowly. Okay, let's do it. The red markers on the Toroflux indicate the 13 loops giving its first torus knot number. I've labeled the markers in the order that we would come across them if we traveled along the Toroflux. Currently, the labels are touching the sheet of plexiglass that I've placed on top. Okay. In fact, as I collapse the Toroflux by pressing down on the plexiglass, these markers will always touch the plexiglass and will always form a circle, even when the Toroflux is fully collapsed, like now. Okay, let me just show you where the markers are now. Okay, zoom in. There they are. To count the coils in this collapse state, we can count along this radius, right? We would basically just do this and then count along there. And what we also see that all the coils that we count this way are as long as the circumference of the circle in front of us. This long, right? However, the distance from marker 1 to marker 2 along the wire is longer than that. Let's just see what it does. To be precise, it's longer by 1/13 of the circumference. And since all 13 distances between consecutive markers feature this 1/13 axis, together these axes add up to the extra 14th coil that we count in the collapse state. And that's how the length redistribution from expanded to collapse state works for the Toroflux. And this also explains why there actually is no discontinuous jump from 13 to 14 coils during our continuous transition. We are really just counting different things. Paradox solved. I made the very nice torus knot pictures with the amazing software package Notplot. If you're not familiar with it, definitely check it out. And here's what the Toroflux looks like in Notplot. I own about 10 Toroflux toys, all made by different companies. The torus knot numbers differ slightly from toy to toy, but for each toy, its two numbers differ by 1, as in the example I showed you. So, a natural question to ask is whether it is possible to build a functioning Toroflux with a different difference. For example, a Toroflux based on this torus here, whose numbers are 13 and 15. What do you think? I could go on for hours talking about other amazing mathematical appearing, disappearing acts involving infinity, higher dimensions, and so on. But let's call it a day with one last particularly nice trick. Fully animated, and it's got funky music again. And that's it for today. Time for me to vanish.